In our today's lecture, we will study about the applications of Gauss law. Now, earlier we have studied about the continuous charge distribution, in which we have studied about linear charge distribution, surface charge distribution, and volume charge distribution. Now, we know that the electric field due to discrete charge distribution can be obtained by using Coulomb's law and principle of superposition. But when there is a case of continuous charge distribution, we cannot use the Coulomb's law. So for that, we have to use some other method. And with the help of this Gauss law, we can find the electric field around such charge distribution. So if the continuous charge distribution has some symmetry, then by using Gauss law, we can find the equation of electric field for such charge distribution. Now, first application of Gauss law. Electric field due to an infinitely long, straight, uniform charged wire. Now students, here you can see that there is a wire on which the charge is present. So this is the case of linear charge distribution. Also, a point P is selected around it, which is at a distance r. So from this charged wire, we have to find the electric field at point P. So we know that for linear charge distribution, the charge density is given by lambda. Now, to find the electric field at distance r, we have to consider an imaginary cylindrical Gaussian surface. You can see here around this wire an imaginary cylinder is drawn. This imaginary cylinder is called the Gaussian cylinder. Now, electric field due to this charged wire is radial, means it is normal to the wire in all the direction. So now for this Gaussian cylindrical surface, we know that there is an upper part, a lower part, and the curved surface. Now for this upper plane surface, which is circular, and even for the lower plane surface, the flux linked will be 0, because here the area vector for this surface is in this direction and the electric field is in this direction. So this area vector for this surface and electric field, they are perpendicular to each other, and so angle made is 90 degree, and hence cos 90 is equal to 0, and so the flux is not linked with this surface and the lower surface, and so now only one surface is remained, that is this curved surface. Now for this curved surface, at any point the electric field due to this charged wire as well as the area vector both are in same direction, and so angle made between these two vectors will be 0, and cos 0 is equal to 1. So we can say that the flux linked with this Gaussian surface is only with the curved surface. Now let us see the calculation part. Here I have written that flux through the two ends of the cylinder is 0. Let us consider that flux related with that two circular ends as phi 1. So our formula for the flux is E dot S. Here S1 means that circular surface is of a cylinder, but as this E and S1 they are perpendicular to each other, the result will be 0, and so the flux linked with that two surface phi 1 is 0. Now flux linked with the curved surface, let us denote that flux by phi 2. Again the formula for the flux is E dot S. Here S2 means for curved surface. Now E dot S, when we remove the dot product, we know that there is a cos theta, but here cos theta is 0 because electric field is parallel to the surface, and so cos 0 becomes 1, and so only remain is E S2. Now we know the formula for the curved surface area of a cylinder, and that is 2 pi r L, where this L is nothing but it is length of the cylinder. So here we obtained the flux linked with the curved surface. Now finally the total flux. So total flux is nothing but the flux linked with the top and the bottom circular parts, which is 0, and the flux linked with the curved surface. So we have added these two flux, but as this is 0, the total flux is contributed only due to the curved surface, which is this, and so the total flux is also this, that is E into 2 pi r L. So here we have obtained the flux, and let us give that equation number 1. Again, according to Gauss law, flux phi is equal to total charge upon epsilon naught. Now here we know that the case is of linear charge density. According to the definition of linear charge density, lambda is equal to total charge upon length. So if we'll make the subject Q, we'll get Q is equal to lambda. So here we have placed that Q, which is equal to lambda. So this is also flux for the same situation, and so here we have given this equation number 2. Now equation number 1 is also of the flux, equation 2 is also for the flux only, and so if we'll compare these two equations, then we will get E into 2 pi RL is equal to lambda L upon epsilon naught. So comparing these two, you'll get this term, and then if we'll make the subject E, then we'll get this final equation. You can see here L on both the side will cancel out, and if we'll bring this 2 pi r in the right side, we get this equation. Now this equation 3 can be written in a vector form as vector E is equal to same this thing as it is, but here we have to put a unit vector for the direction of this electric field. Now here this n means it is normal to the wire. You can see here written that what is n. So n is a unit vector which is always used for the direction, is in the direction normal to the surface at a point P, radial unit vector. From figure also you can see that here in figure we have obtained the electric field at point P, and we know that from this wire this electric field is always radial, so that electric field pass through this point along this line. So we can say that it is along the radial direction. Also we can see that for this curved surface this vector is normal to the surface, and so the direction of the electric field will be this. If we have selected any point here, then the direction of electric field will be in this direction. In this equation of electric field, lambda is a constant as well as these values are constant. So we can say that the electric field for linear charge distribution is inversely proportional to R, that is E is proportional to 1 by R, means if the distance increases electric field will decrease. Now to remember this formula in easy way, if we multiply 2 in numerator and in denominator, then in denominator you will get 4 pi epsilon naught. 2 is here, and you know that 1 upon 4 pi epsilon naught is nothing but it is k. So this formula can be easily remembered by this form. It is 2k lambda by r, where k is 1 upon 4 pi epsilon naught. So here we have studied about the electric field of a linear charged wire. Now our next topic is about the electric field due to uniformly charged infinite plane sheet. The first case was of about linear distribution. The second case is about the surface charge distribution. Now we know that for the surface charge distribution, the density, that is charge density related to it, is called surface charge density, which is denoted by sigma. Now here you can see from the figure that a plane surface of infinite length is given and the charge is present on this plate. Now you can see that this plane surface is lying in YZ plane, and so x-axis is along the normal to this plane. Now here we have considered a Gaussian surface. You can see that this cubical shape, here the name of this cubical shape is given as parallelopiped. So this imaginary parallelopiped is passing through this surface. In earlier case, that is for the linear charge distribution, we have considered a cylindrical Gaussian surface. But here we have considered this parallelopiped as a Gaussian surface. You can see here this is a parallelopiped which is passing through this charged plane. Now we know that for this parallelopiped there are 6 faces. Out of that 6 faces, the flux is linked with the 2 faces only, which is on the left side and the other on the right side. The rest of the 4 faces do not contribute to the flux. So here I have named these 2 faces as phase 1 and phase 2. So flux linked with these 2 phases will contribute the flux of a total parallelopiped. Now see this calculation part. The total flux linked phi is phi 1 and phi 2, that is on the left surface and on the right surface. The flux linked with that 4 surfaces is 0, which is lateral surfaces. So now we know that the formula for the flux phi is equal to E dot A, but as from the figure it is clear that the flux linked with this phase as well as this phase are equal, and so here we have put twice of E dot A. Now as the electric field and the area vector are in same direction for this surface, so angle made between this electric field and area will be 0, and so cos 0 is 1, and so we can simply remove this dot product and write EA. Here I have mentioned that electric field and area vector, they are parallel to each other. So we can say that the total flux linked with that parallelopiped is 2EA. Let us give this equation number 1. Now using Gauss law, flux phi is total charge enclosed upon epsilon naught. Now here the total charge enclosed by this parallelopiped will be this much, as this parallelopiped is passing through this plane surface and it passes through only this much part. So the total charge enclosed is considered this only. So here we have taken phi is equal to q by epsilon naught. Now we know that for the surface charge density sigma, according to definition, it is q by a. So here if we'll make the subject Q, we get Q is equal to sigma into A. So here we have placed the value of Q, which is sigma A. Let us give this equation number 2. Now here this equation number 1 is also for the flux, even this is also for the flux, and so comparing these two equations we get 2EA is equal to sigma A upon epsilon naught. Now both the side AA cancel, and now making subject E, we get E is equal to sigma upon 2 epsilon naught. So this is the equation of electric field for the surface charge distribution. The same equation can be written in a vector form. If there is a vector here, then we have to put the unit vector which shows the direction. So here also, as we kept vector here, we have to show the direction, and here the direction is shown by the unit vector, and the direction of this unit vector is normal to the plane going away from it. From figure also you can see that here at this point the direction of electric field will be along the normal to the plane. You can see this line is normal. If we have selected any point here, then the electric field at this point will be again normal to the plane in this direction. So electric field due to infinite plane surface will be like this. On right side and on left side it will be like this. That is, uniform electric field is there. You can see these lines of electric field are parallel to each other, and when these lines are parallel, we can say that the electric field is uniform. And in a uniform electric field, thus the magnitude of electric field will not depend on the distance. If we'll select any point here, then also the magnitude of electric field will remain same. That means it does not depend on the distance. For less distance also the electric field is same. For the large distance also the electric field is same. And so the formula also indicates that this electric field does not depend on distance, because this sigma is also constant, as well as in denominator this 2 and epsilon naught, that is also constant. So electric field due to a plane charge surface does not depend on the distance.